This video will demonstrate how to use T-Slope to begin with a 2D slope stability problem and convert and solve it in 3D also. As indicated, the example is one described by Duncan et al. Their example 3, excavated slope in a stiff-fissured clay. In preferences, the default units need to be changed from metric to US customary as we're working in feet and pounds. Moving down the navigation tree, we can define the materials. Working from the top down, firstly we have the clay fill. We set the values here as per the table from Duncan. We add a new material and set values for the marsh clay and again for the London clay. Note that the London clay unit has a cohesion that varies from datum rather than a constant, so has a few extra variables that need to be entered. Now we come to defining the surface. The top surface is the excavated surface, which we can create by adding an extruded section. The default section here is a simple plane, but we can manually enter the X and Z points as defined by Duncan or import them from a file. And by default, the plane has a width in the Y direction to give it 3 dimensions, as shown here. Our next step is to create layer surfaces for each of the units in the problem. Again, we will add extruded sections for these and add points that define the top of each layer. By default, the bottom of the layer is automatically set to the top of the one below, and the lowest layer will extend below the limit of the model. For each layer, we must select the material type for that layer, and to keep in line with the original example, we can change the color surface to something similar to the figure. By changing the opacity to 80%, we will be able to see through the layers to the excavated surface on our screen. All 4 layers are created in the same way, so we have sped through them here in the video. A 2D slope case is built from a defined cross-section, so we move to adding a cross-section to our project. In this case, the section is exactly where we need it, but it can be adjusted by moving the nodes or typing start and end points. When we then add a 2D slope, we are presented with a dialog box where we can select section line and surfaces. We will take the defaults. The first thing you will notice is the addition of a new surface in your project. This is a basal surface that will store the location of the critical circle for this slope. When viewing it in the cross-section plane, we can see that by default it extends across the full section. We know the failure circle will more likely end at the toe of the excavated slope and begin in a zone closer to the top of the slope, so we can move the exit points of the circle to reflect this. We also know that in this example, the clay fill layer provides no cohesion, and therefore the top of the critical circle will be at the boundary between the fill and the marsh clay layer. We can simulate this by adding a tension crack with a depth of 11.5 feet, which is the thickness of the fill layer. When we select Solve, we can watch the iterative process that is being undertaken. The program firstly finds the critical circle using the ordinary method of slices, then proceeds with the calculations using Spencer's method. Before long, we are shown the critical circle and its factor of safety, which in this case is 1.77. We also have a calculated line of thrust, the red line, and the normal stresses acting at the base of each slice, the scaled black arrows. Using the critical circle found during the 2D analysis, we can generate an ellipsoid that is required to carry out our 3D slope analysis. Firstly, we duplicate the 2D circle. Then in the new surface, we can rename it, unlock and adjust the geometry to create an ellipsoid by moving the nodes. Note that we're not altering the surface in the slope failure direction, only in the width. When we then add a 3D slope, we are again presented with a dialog box where we can select the surfaces. We will accept the defaults. The 3D gridded model is displayed. The columns involved in the analysis are shaded a darker color. This is more easily seen if we turn layer coloring off. We can increase the number of columns to help reduce any edge effects during analysis, and we can use slope clipping to trim the model area down to fit around those darker columns and reduce the number of columns within our analysis area but outside of our model area. In this slope, we also need to take care at the toe to exclude those columns further out. We must apply the changes before we can then solve this scenario. The 3D slope case has a factor of safety of 1.95. This is slightly higher than the 2D slope case. Using the View and Data menus, we can graphically display the values at the base of each column within the model. These can help us picture the variations in stresses and local factors of safety across the model. The images can also be saved as snapshots if required to go into your report.